Lesson 11, Radiographic Testing. Introduction to Radiographic Testing. Radiographic testing, abbreviated RT, is the testing of a structure or material using ionizing electromagnetic radiation comprised of either X-rays or gamma rays to produce radiographic images for visual evaluation. Although RT is highly beneficial to numerous industries and able to visualize numerous hidden discontinuities, it does not come without inherent safety risks. X-rays and gamma rays cannot be detected by any of the human senses, yet radiation can be very dangerous without the proper precautions. Radiographic testing's use of ionizing electromagnetic radiation can cause serious damage to tissue and cells due to the ionization process, which changes the body's biological chemical bonds and releases free radical ions to create undesirable chemical bonds and permanently damage the DNA, RNA, and protein of living organisms. Extremely high single doses, or the accumulation of smaller unsafe doses of ionizing radiation, can lead to radiation sickness or even death. For this reason, regulatory controls are established, such as those imposed by the U.S. Nuclear Regulatory Commission to govern the use of ionizing radiation. Advantages of radiographic testing. A permanent record of the inspection is created. It can be applied to most types of materials. Internal structural discontinuities can easily be located. It provides a universal approach to volumetric examination. It provides a visual rendition of internal voids and fabrication errors. It can provide a digital record of the test object for computer monitor display. Limitations of radiographic testing. It is a relatively expensive non-destructive testing method. It is impractical to use on specimens of complex geometry. Discontinuity orientation to the radiation photon path is critical. There must be access to both sides of the test object. Extensive training and proficiency is required. And radiation hazards exist that require operating license. Fundamental properties of matter. To fully understand radiography, it's important to be generally familiar with the origins of radiation and how radiation interacts and affects material at the atomic level. At its most basic level, matter can be defined as anything that has a mass and occupies space. Matter exists in many different forms and is made up of countless tiny particles called atoms. Atoms are building blocks of all matter and are composed of space more than anything else. Within the vast space are three basic parts: protons, neutrons, and electrons. Protons and neutrons are at the center of the atom, called the nucleus. Protons have a positive electrical charge, and equally sized neutrons have no electrical charge. Electrons are substantially smaller than protons and neutrons, are negatively charged, and revolve in orbit at incredible speeds in the space around the nucleus in cloud bands called shells. Atoms have an equal number of protons and electrons. The number of protons determines the atom type. What differentiates one form of matter from another is the type of atom it is composed of. Matter that is composed of only a single type of atom is identified as an element. The periodic table of elements identifies all the known element types. The number on the top of each element signifies the number of protons and equal number of electrons. There are 118 known elements organized by the atomic number, meaning the number of protons. As an example, all hydrogen atoms have 1 proton and 1 electron, and all tungsten atoms have 74 protons and 74 electrons. The rows in the periodic table of elements provide information on how many shells an element atom has. The top row has 1 shell and increases 1 shell per row down the table. As an example, hydrogen has just 1 proton and 1 orbiting electron in 1 shell. Helium has just 1 shell as well, but has 2 protons and 2 electrons. Tungsten, on the other hand, has 6 shells to systematically hold in orbit all of its 74 electrons. All atoms have electrons that revolve around the nucleus inside shells. Electron shells are lettered K through Q, or numbered 1 through 7. Each shell is limited to a specific number of electrons depending on the element. If one were to take a basic illustration of an atom and flatten it, it would show how the electron orbit shells are arranged around the nucleus. Electrons in the K shell, closest to the nucleus, have a much greater strength to remain in orbit. The further away from the electron shell, L through Q, the less orbit binding strength the electrons have. Molecules and mixtures. Nature and human intervention both have the ability to combine or mix atoms to realize the abundance of matter. If individual atoms chemically bond with another atom by sharing their electrons, it is called a molecule. Molecules made up of the same atom types bonded together are still called elements. Molecules may be simple or complex. The combination and mixture of atoms and molecules can produce countless different materials. The last type of matter is two or more substances blended together to make a mixture. Mixtures can be heterogeneous or homogeneous. The difference is the degree in which materials are mixed and their composition uniformity. A homogeneous mixture is equally blended where the composition is the same throughout. Some examples include cola soft drinks, salt water, air, and metal alloys such as brass. A heterogeneous mixture is blended where the individual mixed components can easily be identified. Examples include concrete, sand and dirt mixtures, and oil and water mixtures. Isotopes. If atoms of the same element have a different number of neutrons, the mass number will change and create what is called an isotope. The number of neutrons a nucleus can hold differs from element to element. Some isotopes are stable and others are unstable. Most of the time, simple elements have the same neutron number as proton number, but in the heavy elements, more neutrons are present than protons. The number of neutrons is important to balance the stability of the nuclei. Radioisotopes. Isotopes that are radioactive are called radioisotopes. Typically, most atoms have a stable nucleus. However, as the ratio of neutron to proton imbalance increases, the nucleus becomes unstable and emits radiation in an attempt to become stable. This stability process is known as radioactive decay. When nuclei are too heavy, they become unstable. Those isotopes therefore become radioactive. For example, hydrogen has three isotopes called protium, deuterium, and tritium. Tritium is considered radioactive. Types of radiation. The major sources of radiation include particulate radiation of alpha, beta, and neutron particles, as well as electromagnetic radiation from gamma and X-ray sources. All these radiation sources are created by unstable atoms that must release energy or mass in the form of radiation to become stable. Alpha particulate radiation. Alpha radiation is comprised of high-speed, positively charged particles produced when the heaviest elements decay. Alpha radiation particles are made up of two protons and two neutrons held tightly together and are expelled from an unstable atom's nucleus during its transition into a stable atom. This phenomenon is known as radioactive decay. Alpha particles are emitted from naturally occurring materials, uranium, radium, and thorium, and manufactured elements like plutonium and americium. Although they travel extremely fast, alpha particles are relatively large and heavy. As a result, they do not travel very far, maybe a few centimeters at most, have poor penetrating ability, and are easily stopped. A sheet of paper or an inch of air is more than sufficient to stop alpha particles. Alpha particle radiation is not used for industrial radiography, however it can be found in smoke detectors in very minute amounts. Alpha radiation is generally not hazardous to humans since the particle is blocked by dead skin cells. However, if any alpha particles are ingested or inhaled, serious cell damage could occur to internal body tissue. Beta particulate radiation. Beta radiation originates from radioactive decay in which an electron is emitted from a radioactive or unstable atom's nucleus. Normally, an electron orbits the nucleus. To differentiate these radioactive electrons from the nucleus, they are referred to as beta particles. Beta radiation is composed of high-speed, negatively charged free electrons emitted from the atom's nucleus having excess neutrons. The unstable atom must transition into a stable atom to restore energy balance. In doing so, it ejects an electron as part of the radioactive decay. Beta particles are much lighter, smaller, and faster than alpha particles, and thus have more penetrating ability. However, beta particle radiation is not used in non-destructive testing applications. Beta radiation can be hazardous to human health, as it can penetrate the skin and cause skin and cell damage. However, very thin sheets of aluminum and wood can stop beta particles. Neutron particulate radiation. Neutron radiation consists of free neutrons, meaning they have no charge, emitted as a result of nuclear fission, where the atomic nucleus is splitting. These free neutrons are capable of traveling hundreds of meters in air, but can be stopped by matter that is hydrogen-rich, such as water and concrete. Neutron particles get absorbed into stable atoms, which makes them unstable, thusly emitting ionizing radiation. This is the only type of radiation capable of turning other matter radioactive. Neutron radiation is extremely dangerous and typically used only in very limited applications such as nuclear reactors, where water and concrete shield the radiation from the public. Neutron radiation is also used in nondestructive testing and comprises its own method called neutron radiography. Gamma ray radiation. Gamma ray radiation is an energy photon emitted from the nucleus of unstable isotopes. The emission of gamma rays does not alter the number of protons or neutrons in the nucleus, but instead has the effect of moving the nucleus from a higher to lower energy state, from unstable to stable. Gamma ray emission frequently follows beta decay, alpha decay, and other nuclear decay processes. Gamma radiation has neither mass nor electrical charge. Gamma radiation travels at the speed of light and at a greater distance than alpha or beta particulate radiation. Gamma waves penetrate most matter but can be stopped by dense or a high atomic number material, such as lead, depleted uranium, and very thick steel. Gamma ray radiation can be used for radiographic testing and is most applicable in remote areas where electrical power to produce X-rays is not practical. X-ray radiation. X-rays are similar to gamma radiation, with the difference being that they originate from a tube head powered by electrical current versus a radioactive source. X-rays are emitted from the tube head due to high-speed electrons being suddenly stopped by a tungsten target. X-ray tube heads provide a means for producing, accelerating, and suddenly stopping electrons. The kinetic energy of the high-speed electrons being suddenly stopped converts to heat and X-ray photons. Unlike the steady stream of photons from gamma ray sources, X-rays have controls to vary in quantity and energy intensity. The two primary X-ray emissions of photons come from Bremsstrahlung radiation, meaning breaking radiation, and K-shell emission radiation, also known as characteristic radiation. Bremsstrahlung radiation. X-ray tube heads produce X-ray photons by accelerating a stream of electrons and colliding them into a tungsten target. The abrupt deceleration, where the electrons may stop, slow, or change direction, produces Bremsstrahlung photons. X-ray radiation with a continuous spectrum of energies is produced from 0 to a maximum equal to the energy of the electrons striking the target. K-shell emission radiation, also known as characteristic radiation. The K-shell is the lowest energy state of an atom and closest to the nucleus. An incoming electron from the tube head stream of electrons can give a K-shell electron enough energy to knock it out of its energy state. Then, a tungsten electron of higher energy can fall into the K-shell. The energy lost by the falling electron shows up as an emitted X-ray photon. Meanwhile, higher energy electrons fall into the vacated energy state in the outer shell, and the cycle keeps repeating. K-shell emission produces higher intensity X-rays than Bremsstrahlung, and the X-ray photon comes out as a single wavelength characteristic radiation. Interaction of radiation with matter. Photons. The quantity of photons traveling through a material depends on the thickness, density, and atomic number of the material, as well as the energy of the individual photons. X-ray or gamma ray photons will do one of two things when they travel through matter. They either travel completely through the material without any particle interaction in their path, or they collide with particles in their path, whereby their energy is either absorbed or scattered, which is known as attenuation. Attenuation. Attenuation is when the energy of colliding photons is either absorbed or scattered. Attenuation creates a loss of energy due to the excitation or ionization of atoms in a photon's path. Excitation of atoms occurs when electrons absorb energy from a passing radiation photon particle but are not removed from their atom. Excited electrons can produce radiation energy during the process of returning to a lower energy state. Attenuation characteristics either increase or decrease as the radiation energy is increased or decreased. Ionization, on the other hand, occurs due to photons impacting the matter's atoms in their path and dislodging the atom's electrons. Attenuation characteristics either increase or decrease as the radiation energy is increased or decreased. Since attenuation characteristics of materials are important in the development of contrast in a radiograph, an understanding of the relationship between material thickness, attenuation properties, and photon energy is fundamental in producing a quality radiograph. Contrast is defined as the differences in radiation pattern intensity after passing through an object. A radiograph with higher contrast will provide greater probability of detection of a given discontinuity. Depending on the test specimen material, meaning the atomic number, density, and thickness, and the quantity and wavelength of the radiation photons, the excitation and ionization can unfold in three distinctive ionization processes, known as the photoelectric effect, Compton effect, and pair production. The photoelectric effect. The photoelectric effect occurs at lower energies, 0.01 to 0.3 megaelectron volts or MeV, when radiation photons enter matter with atoms of a higher atomic weight. The photons encounter and are absorbed by a K-shell electron. The electron's new kinetic energy, which is transferred from the photon, imparts velocity and knocks the electron from its orbit. These ejected electrons are called photoelectrons. The K-shell now has an electron void that must be filled. An outer shell electron moves inward to fill this void and releases its excess energy as lower energy, characteristic radiation. Compton effect, also known as Compton scattering. The Compton effect has higher probability of occurring when mid-range energy, electromagnetic radiation photons enter matter and encounter an outer shell electron in their path. The radiation photons are deflected when they collide with the electron. The electron gains some of the photon's energy and is ejected from its orbital position, while the radiation photon loses some of its energy but continues to travel through the material along a deflected path with a longer wavelength. This process continues until the photon energies decrease to a level at which the photoelectric effect occurs. The Compton effect creates scatter radiation and can hinder the radiographic image-making process in three ways. 1. Through reflective scatter, caused by objects, walls, tube head, stand, and so on, in the radiation beam path. 2. Backscatter, caused by objects that are behind the film, such as the floor, secondary structures, and so on. 3. Undercutting. At the edges of a part, the scattered photons originating inside the part have less material to pass through and so are less attenuated. Pair production. Pair production occurs when high-energy photons, typically greater than 1.02 MeV, enter the nuclear field, the space between the nucleus and electron K-shell of the atom, of a material with a high atomic number. The photon is absorbed by the nucleus while its energy produces both an electron and a positron pair of equal energy levels greater than 0.51 MeV. At 0.51 megaelectron volts, the electron and positron pair is without velocity, but at levels greater than 0.51 MeV, the positron and electron gain the velocity needed to travel and interact further in the material. The newly formed electron is ejected from the atom, while the slow-moving and short-lived positron may cause ionization or may combine with an electron, causing annihilation and emission of 2 gamma photons of 0.51 MeV per photon. These lower energy photons may subsequently have multiple interactions with electrons and undergo either the photoelectric or Compton effect absorption modes as travel distance and energy levels subside. Exposure devices and radiation sources. The major sources of radiation used to produce radiographs are X-ray machines and gamma rays produced through the disintegration of unstable radioisotopes. X-radiation sources. X-ray production. Machine-generated X-rays are powered and controlled by electrical energy. The exposure time and source energy levels are set to permit the radiation passing through the test item to create a latent image of the test part on the film. X-ray production can produce a large range of energy levels to penetrate the thicknesses of materials found in industrial practices. To generate X-rays, 3 things need to happen. There must be an electron source. These electrons must be accelerated, and the accelerated electrons must then be suddenly stopped. These three components all occur in an X-ray generator device called a tube head within the cathode and anode. The cathode. The negatively charged cathode is made up of thin tungsten wire, also called a filament, that heats up as electrical current flows through it. As the filament heats up, the tungsten electrons get more and more excited and escape the material to form a highly enriched electron cloud around the filament. A focusing cup corrals the filament and electron cloud to concentrate the steady stream of electrons flowing towards the anode. The anode. The positively charged anode is made of a material with a high thermal conductivity, typically copper, to help with heat dissipation. The anode has a very high positive charge during operation to forcibly attract the electron cloud from the cathode's focusing cup. These electrons travel extremely fast from the cathode to the anode to strike a tungsten target embedded in copper at approximately 20-degree angle. The target's tungsten and copper materials are chosen for their high atomic number, high melting point, high thermal conductivity, and low tendency to vaporize. These qualities of tungsten and copper allow the target to withstand a great deal of heat, dissipate that heat, and minimize target material that is vaporized. The target has a focal spot that is the epicenter of the electron bombardment. Due to the target angle, the effective focal spot is only a small fraction of the actual focal spot and directly impacts the X-ray image quality. The smaller the focal spot, the better the detail and sharpness of the radiograph. Both the anode and cathode are encapsulated in high vacuum envelope to provide electrical insulation and reduce interference with air molecules before electrons have an opportunity to collide with the target. Tube head controls. The milliamperage. In generating X-rays, the tube head has two adjustable controls to optimize X-ray energy intensity and quantity. The milliamperage or MA control adjusts the tube current by increasing or decreasing electrical current to the filament. As milliamperage is increased, the filament gets hotter to form a more concentrated electron cloud. The more electrons available, the greater the quantity of X-rays that can be produced. Kilovoltage. The kilovoltage, abbreviated kV, controls the tube voltage by increasing or decreasing the electrical potential difference between the cathode and the anode. As kilovoltage is increased, the electrical potential difference accelerates the electron stream from the cathode focusing cup to the anode's target. As the most important variable in radiographic operations, the kilovoltage controls the energy intensity of X-rays. As kilovoltage increases, radiation energy intensity and penetrating ability increase. Gamma radiation sources. Gamma ray radiography is very similar to X-ray radiography. In field applications, reliable sources of electrical energy may not be available, so radioactive isotopes are used to provide gamma radiation in lieu of the X-ray tube head. The exposure is controlled by the activity of small pellets of radioactive material and the time during which it is removed from its highly shielded chamber, called the exposure device or camera, to penetrate the test item. The nature of the radiation available for gamma ray radiography is restricted by the availability of the types and sizes of isotopes. Radioactive decay. When radioactive elements decay, they can emit photons at energies useful for industrial radiography. Several radioactive elements have specific activity high enough to be practical sources for radiography. The number of radioactive atoms, or the number of atoms decaying per unit of time, changes exponentially with time. Radiation emissions from radioactive isotopes takes life away from the isotope, similar to how, as humans grow older, they have less energy. In gamma radiation, this reduction of radioactive energy over time is called the half-life. The half-life is the time required for half of the original number of atoms to decay. Radioactivity measurement. The becquerel, abbreviated BQ, and the Curie, abbreviated CI, are two common measuring units to express radioactive material activity. The becquerel is the metric unit to describe one disintegration per second. The Curie is the number of disintegrations occurring per unit of time, 3.7 times 10 to the 10th atoms per second. The specific activity of a radioactive source is its activity per unit mass. The higher the specific activity, the greater the radiation intensity per unit mass. Multiplying by the material density provides the activity per unit volume, which is important for the radiographic sources, as source size affects image resolution. Of the several hundred known radioactive isotopes, only a handful of artificial radioisotopes have become widely useful for radiography. The remainder are unsuitable for a variety of reasons, including a very short half-life, unacceptable radiation or energy, low available intensity, and high cost. A few artificial radioactive isotopes that are commonly used in industrial radiography are cobalt-60, abbreviated CO-60, which has a half-life of 5.3 years, iridium-192, or IR-192, with a half-life of 75 days, and selenium-75, abbreviated SE-75, with a half-life of approximately 120 days. Each isotope is useful for different applications. Cobalt-60 is useful for radiographic applications of thicker, usually greater than 1 inch thick, medium-weight metals such as iron, brass, and copper. Iridium-192 is used widely for the radiography of steel that is 0.75 to 3 inches in thickness. Selenium-75 has a much lower energy and is good for thinner materials of less than 1 inch thick. Isotope source radiation. You would think that the physical size of radiation isotopes would be fairly large to have enough power to penetrate metals, especially metals that are many inches thick. Surprisingly, isotope pellets are very small, roughly the size of a grain of sand. These pellets are enclosed in a welded stainless steel capsule and attached to a flexible cable called a pigtail. The isotope capsule and pigtail are secured in a shield housing, sometimes called a camera. When radiation is needed for an RT application, the isotope is cranked out from the shielded housing unit through a guide tube. The radiation is emitted 360 degrees from the isotope pellet. To limit the unwanted radiation not used for the inspection, the guide tube often has a collimator at the end to shield the radiation, except in the direction necessary to make the RT exposure. Once the exposure time has lapsed, the isotope is cranked back through the guide tube until it enters and is secured in the shielded housing. The inverse square law. Regardless which radiation-producing device is used, an X-ray tube or an isotope source, the intensity of the radiation reaching an object is determined by the radiation travel distance. Radiation rays behave very similar to light. As the rays are emitted from the radiation-producing device, they diverge and spread out over an ever-increasing area with lessened intensity as they travel from their source. This principle is known as the inverse square law. The inverse square law equation is intensity 1 divided by intensity 2 equals distance 2 squared divided by distance 1 squared, where intensity 1 is the radiation intensity at distance 1, intensity 2 is the radiation intensity at distance 2, d sub 1 is the distance at intensity I sub 1, and d sub 2 is the distance at intensity I sub 2. Radiographic image acquisition. Radiography requires a medium on which to capture a test specimen image for viewing and evaluation. Up until the 21st century, the predominant image acquisition technique was film radiography. However, as computer and medical radiographic technology evolved, so did digital radiography, abbreviated DR, and computed radiography, abbreviated CR, techniques for industrial applications. Regardless of what media captures the image for viewing, the radiographic setup follows virtually the same 5-step process. 1. The radiation source, whether it's X-ray or an isotope, is directed towards a test object. 2. The radiographic image medium, whether it's film, cassette, or digital sensor, is placed behind the test object. 3. An appropriate amount of time is allowed for enough radiation to pass through the test media to the radiographic image media. 4. The radiographic image medium is processed. And 5. The radiographic image is evaluated. Film radiography. Radiography using X-ray film is the traditional technique of image acquisition. Modern radiographic films consist of a thin, flexible, transparent polyester plastic base material that is sandwiched between a very thin emulsion gelatin coating containing a radiation-sensitive silver halide compound, such as silver bromide or silver chloride. When X-rays, gamma rays, or light strike the grains of silver bromide compound, a change takes place in the physical structure of the grains. This change is not visible until the exposed film is treated with a chemical solution to create a chemical reaction that forms black metallic silver. It is this blackened silver suspended in gelatin that gives a radiograph its contrasting grayscale image. Film radiography setup. As radiation passes through the metal part, radiation photons reach the film in more abundant numbers in areas where a void, cutout, crack, and so on exist. In areas that are homogeneous, and especially where denser inclusions are found, less radiation photons will reach the film. When viewing the film, areas that have less attenuation will appear darker or perhaps even black. In areas that have more attenuation, the film will be various lighter shades of gray or even clear. Exposure charts and characteristic curves. The balance between radiograph quality and exposure time is important. If high quality is the deciding factor, a slower, fine-grained film is preferred over a fast, coarse-grained one. If short exposure times are essential, a faster film should be used. X-ray exposure charts and film characteristic curve charts are used by radiographers to aid in decision-making without wasting time and resources with trial-and-error experiments. Image quality indicators. Usually an image quality indicator, or IQI, is placed somewhere on the test object to be viewed on the image after development. The detection of an IQI feature, either a certain size wire or hole in a shim, indicates that the desired required radiographic quality level has been achieved. Film processing. After the radiographic operation, the radiographic film requires processing in a darkroom through a series of 5 steps to physically view the image. Film development requires a specific set of parameters to ensure that chemical concentration, temperature, time, and physical movement are all quality controlled. Processing film can be done manually or with an automatic processor using the same 5 steps. 1. Development. The developer converts all silver halide grains that were exposed to radiation to metallic silver. 2. Stop development. A stop bath of water or acidic solution stops the development process by diluting and rinsing the developer solution. 3. Fixing. The fixer dissolves and removes the undeveloped silver halide crystals, which fall away from the film surface, leaving just the metallic silver on the film. 4. Washing. The film must be thoroughly washed to remove residue chemicals. 5. Drying. The film has to be dried prior to viewing and storage. Computed radiography. Computed radiography, abbreviated CR, uses a reusable phosphor plate or cassette in lieu of film. During an RT procedure, the radiation passes through the test object and is absorbed in the phosphor plate cassette to form a latent or hidden image. The imaging plate is inserted into an image reader machine that houses a laser to excite and illuminate the phosphor plate to expel photons of light. The emitted light from the latent image is detected, captured, and converted into electronic signals as a digital image for viewing on a high-resolution monitor. The digital image file can then be enhanced, scaled, and filtered for preferred contrast and resolution. Images can be stored, accessed, and shared via computer. After the latent image is extracted from the imaging plate, the data is erased and the cassette or imaging plate is ready for another radiographic exposure. As a general rule, computed radiography is advantageous over film radiography for a number of reasons. You have a reduced manpower and material costs. Reduced radiation intensity is required. Reduced time to produce a latent image. Improved image quality and on-demand image optimization. Less floor space is required. There's no need for a darkroom and no film physical storage or archive. CR images can be shared electronically across the globe instantly. There's a wider range of exposure latitude, meaning the film density. And you have improved discontinuity resolution and evaluation. Limitations of computed radiography. Imaging plates are fragile and expensive. Evaluation of images using software tools has a fairly steep learning curve. And overuse of software tools on every radiograph may actually slow production. Digital radiography. Another technique to capture a radiographic image in near real time is digital radiography, abbreviated DR. DR uses a fixed flat panel radiation detector, typically called a digital detector array, that has an array of pixels that convert X-ray energy to an electrical charge. The electrical charge is sent to a processor that assembles an image as a digital file similar to film or computed radiograph. In areas that are homogeneous, and especially denser areas such as inclusions, fewer radiation photons will reach the detector to fluoresce. Since software can manipulate the grayscale, the digital radiograph has endless possibilities of variable image views. Advantages of digital radiography: reduced manpower and material costs, reduced radiation intensity required, reduced time to produce a latent image, improved image quality and on-demand image optimization, less floor space required, no darkroom and no film archive or storage. DR images can be shared electronically across the globe instantly. Wider range of exposure latitudes. Improved discontinuity resolution and evaluation. And no scanning step as with CR. DR images are directly downloaded. Limitations of digital radiography. The initial investment and maintenance of the equipment. Learning curve of image evaluation and overuse of software tools may actually slow production. DDAs have a limited lifespan and can be saturated if radiation levels are too high. DDAs are typically rigid panels that cannot be formed around objects. Because more images can be taken quickly, there is also a possibility of taking more images than needed, requiring more time to interpret. And that concludes this lesson.